Hello everyone, this is Professor Brian Macon, bringing you another calculus video. I am your interpreter of integrals, your calculus connection, coming at you live from the Math Fun Room. So in this section, we're going to look at one of the sections that typically come at the end of a conversation on integration. So usually in a textbook, you'll be presented with the 4 techniques of integration, like we've talked about in our prior videos. And then you'll look at a couple applications of integrals. And in this particular video, what we're going to look at is approximating integrals. Now technically, back in a Calc 1 video, we discussed at the very beginning of integration. We discussed using like the left endpoint, right endpoint, and midpoint. So usually integration is presented to you as finding the area under the curve. And that's how we initially interpret integrals. Now there's a lot of other applications of integrals, like finding volumes of rotation, finding surface area, in a physics conversation, finding the work done, finding the length of the curve, which I have videos on all of that stuff, right? So usually though, back in the Calc 1 course, we introduce the idea of an integral by finding the area under the curve. So I'm just gonna draw kind of a generic curve here, right? So technically we estimate that sum, the area under the curve using rectangles. So let's say we do left endpoints for just a moment. So usually in a Calc 1 class, we'll cut the interval, let's say from A to B. Let me switch back to blue real quick. Let's say we're looking from A to B on my graph. Right? So I'm looking from this point to this point. So usually how we would estimate the area under the curve is, let's say we use left endpoint. So we would use the left endpoint to come up to the function and create a rectangle. And so conceptually in a Calc 1 class, what you talk about is that the area of that rectangle is going to be the height of the function at the left endpoint. And then when we repeat that, so the next interval of x values, right, would be our next rectangle. We're going to look between here and here on my x-axis. We're going to use the left endpoint to come up to the function to generate, well, that was a really sloppy line there, to generate the height of that rectangle. So in this interval between this x value and this x value, we use the left endpoint. We come up and we create the height of the rectangle. So for each of these rectangles, we're calculating an area, and it's estimating the area under the curve. And again, what's the area of a rectangle? It's, the height times the width, or length times width, or whatever you want to call those dimensions. So then my next interval, so from this x value to this x value, I use the left endpoint here. I come up to the function, I come out, and there's the height of that rectangle. Height of this rectangle is determined by the left endpoint hitting the function, and so we have roughly that area there. And we would continue that process between this value and this value. We use the left endpoint to come up, determine the height of the rectangle. Another sloppy line there, right? So on and so forth. So we would repeat that. Now, using all of these left endpoints, let's go there, and then I'm going to get kind of lazy, right? And let's say that's our last one. Okay, so these rectangles estimate the area under the curve. So usually what we do then, symbolically, we will say the area is approximately, the length times the width. Right? Again, I don't want to spend too much time on this. We spent a lot of time developing this in the past. So the width of each rectangle is a delta x, and then the height of the rectangle is the function value. And usually what we do symbolically is we say, well, this is the first rectangle, second rectangle, third rectangle, fourth, fifth, and sixth. So we usually say, well, we're going to technically call this the ith rectangle. So for any of the rectangles, and that's supposed to be a subscript, So this is the ith rectangle, and then this is the function value at the ith left endpoint. Right? Again, that's looking kind of sloppy. Right? That's supposed to be a subscript. Right? So there's the function value at the ith left endpoint. Right? So we would basically say we're going to take every function value, the height, times the width, and we would sum those up. We would say as we go from 1 to n, and there would be our approximate area, right? And then usually what we would do in that case is we would take a limit. We would say the area is exactly equal to, and we take the limit as n goes to infinity of that Riemann sum, right? So back in the Calc 1 class, we called this the Riemann sum, and then this produced what we symbolized as an integral. So we said, well, this was the integral of all function values times, some width, delta x. All right, so what we're going to do in this section here where we're approximating integrals, we're going to actually go backwards. So we're going to say, well, we have this integral, and let's pretend, we can't do the antiderivative. Right? So we need to estimate this integral. So we're going to go backwards, and we're going to sum up a certain number of rectangles. So we're going to sum up the certain number of rectangles to estimate that integral. Now, technically, the left endpoint that we just drew is an estimation to an integral. And again, in a Calc 1 class, we learned about that. And then also learned about the right endpoint. We also learned about the midpoint. So usually in this section, you are introduced, you're reminded of those three techniques. So let's do an example where we're going to look at those three techniques. And again, this is a refresher of Calc 1, and then we will introduce the two new techniques we typically see in a section of this nature, which is Trapezoidal Rule and Simpsons Rule. So what I want to do here is let's look at a particular example. Right? So let's consider that we have the function. Let's just do something really simple. Let's say we have the function x squared that we're estimating, and let's say we're going from 1 to 5. Okay? So visually speaking, we are looking at f of x equals x squared. And let's say, here's the graph, y equals x squared. Rough sketch, right? There's my parabola, y equals x squared. And we're going from, let's say, 1 to 5. So we're going from, here's 1, let's say, out to 5. And we want to estimate the area under that curve. So we're going to use left endpoints, we're going to use right endpoints, and we're going to use midpoints. Now I want to be able to sketch these rectangles, so I'm going to kind of zoom in on my graph in just a moment. So remember, back in a Calc 1 class, what we would say is we want the widths of our rectangles to all be equal. So to find our delta x, so let me come back to my red pen here, and let's say we want to do left endpoints. So the first thing we'd have to do is calculate our delta x. So remember, back in a Calc 1 class, right, again, we would say the length of the interval divided by the number of rectangles that we want. So let's say, and I didn't write this on my instructions, I apologize. Let's say what we want to do here is we want to estimate this integral. Right, so we're going to estimate using, let's say, n equals 4 let's say sub-intervals. This is usually the terminology used in every calculus book, right? So we'll use n equals 4 subintervals. Now in this case, that's a rectangle. For a left endpoint, that's a rectangle that we're going to use, right? So when I do my delta x equals b minus a over n, here's my a is 1, here's my b is 5, right? Those are my limits of integration here, 1 to 5. And then my delta x, so I'm going to have 5 minus 1. My n value is 4. Why did I write that? My brain, it's Monday, and what I think and say comes out different on the paper. All right, so there's b minus a over n, 5 minus 1 over 4. So I got 4 over 4, so we got 1. So our delta x is 1. So we want the width of each rectangle to be 1. All right, so I'm going to zoom in a little on the graph. So I'm going to kind of exaggerate the graph here. So go with me for a moment. So I'm going to exaggerate the graph. Here's y equals x squared. And let's say, there's my graph. I kind of zoomed in a little bit, right? So I want to calculate the area under that curve using left endpoints. Right? So we're going to go from 1 to 4. So we just calculated the delta x of 1. So we're going to go from 1 to 2. There's my delta x of 1. And then we're going to go 2 to 3. There's my delta of 1. 3 to 4. And then 4 to 5. I think I just made a mistake verbally, and I said we want to go from 1 to 4. What we want to do is go from 1 to 5. Right? Our integral is from 1 to 5. That's my a and my b. So I'm going to go from 1 to 5. My delta x is 1. Now, if I'm going to use left endpoints, I'm going to come up, use the left endpoint, come out, and there's that first rectangle. And then for the next interval from 2 to 3, I'm going to use the left endpoint, come up to the function, and there's that rectangle. And then the next interval from 3 to 4, I'm going to come up to the function, and then there's that rectangle. And then last but not least, for my fourth rectangle, right, my n equals 4 subintervals, this interval, I'm going to come up, left endpoint, and out. Right? So there's my 4 subintervals, i.e. 4 rectangles for this scenario. So the integral that we're estimating is the integral of x squared. And we're going to calculate the height times the delta x for each of those rectangles. So we're going to say the integral of x squared dx from 1 to 5 is approximated by, so for each rectangle, we're going to have the height. So this first rectangle, the height was evaluated at x equals 1. So we'd have f at 1 times the delta x. Plus, and then the second rectangle, we would have the function value at 2 times its delta x. Right? Then we would have the function value at 3 times its delta x, and then the function value at 4 times its delta x. Right? So again, this third rectangle is the function value at the left endpoint. That's f at 3, and then f at 4. Now, for this particular example, we know what those values are. Right? This is 1 squared. Now I want you to keep in mind the delta x is the same for all of these. So this delta x is 1, this delta x is 1, this delta x is 1, this delta x is 1. So I'm going to factor out that delta x, and then I'm going to plug in f at 1. So for this equation, right, here's 1 squared, and then plus 2 squared, and then plus 3 squared, and plus 4 squared. Right, and again, visually, right, I'm plugging in x equals 1 up here in my left endpoint, and I'm finding the y value, which is 1 squared. I'm plugging in the second interval, taking 2, plugging it in my equation, finding the y value, which is 2 squared on my parabola. Then I get 3 squared and 4 squared. So there's my 4 subdivisions. All right, and then I take out a calculator and I approximate that value, and I get a value of 30. So this is 30. So we're saying that the value of the integral is approximately 30. Now in reality, I don't really need to approximate this integral because I know how to find the antiderivative of x squared. But we picked an easy equation to make this relatively straightforward. So what we could do if we really wanted to is find the exact area, and we'll do that in a minute. Now let's say we want to do right endpoints, right? So let's say we want to do right endpoints. So again, we're estimating the integral of x squared dx from 1 to 5, and we're using, n equals 4 subintervals. So we already did this, right? But my delta x, b minus a over n, was the 5 minus 1 over 4, which was 1. So for this same scenario, my delta x is 1, because we're using the same number of subdivisions. Right? So again, I'm gonna visually kind of exaggerate the shape of this graph. So here's y equals x squared. And let's say we're going to look 1 to 4. Right? So we're going to go from 1 to, dang it, I keep saying that, 1 to 5. All right, now again, my delta x was 1. Right? So there's each of my subdivision values. Right? So in this scenario, I'm using right endpoints. So for this first interval, I'm going to come up and use the right endpoint. And there's my first rectangle. Now, the height of that rectangle is now f at 2. So my integral is going to be approximately, so I'm going to go ahead and factor out my delta x, right, just like we did last time. And the first height is f at 2. Right? So remember, f at 2 times the width. So the area of this rectangle is the height times the width. The width is my delta x. All of the widths are the same. I'm going to factor that out, and then I just have the height of each endpoint. So in this case, the right endpoint is f at 2 for the first rectangle. Then for this next interval, I'm going to come from the right endpoint and out, so that's f at 3. And then for the next rectangle, I'm going to look from 3 to 4. I'm going to come up to the function, and there's the height of that rectangle. And then ditto, I'm going to have f at 5 for that last rectangle, right? So the last rectangle comes up, and there's that rectangle. So there's the area of the 4 rectangles with right endpoints. And then I left off my limbs of integration, I apologize. So my integral is from 1 to 5, and we're saying that that's approximately that value. And again, we know that the delta x is 1. And so now we're plugging into our actual equation. So this is going to be 2 squared, 3 squared, 4 squared, and 5 squared. And if I find that value numeric, I get 54. So if we use left endpoints, what did we get last time? Forget. If we use left endpoints, I'm going to scroll back up real quick. If we use left endpoints, come on, baby, you can scroll for me. If we use left endpoints, we got an estimation of 30. And then if we use right endpoints, we get an estimation of 54. Now, if we stop for a second, right, you usually have this conversation in a Calc 1 class. For this particular shape of graph, because it's, it's increasing, right, the right endpoints have extra area. Here's some extra area. I have some overhang, if you will. So this is an overestimate. And then if we come back to the left endpoints graph, we can see that all of these rectangles have some underestimate. We have some pieces that are under the curve. So the 30 value that we got here is an underestimate. So we're somewhere in between 30 and 50. So final conversation here. Right? Usually, here's my right endpoint. Usually, in a Calc 1 class, what you do is you say, well, you know what? If we use the midpoint of each rectangle, this is actually going to be a little bit more accurate. So let's come back and look at the midpoint of each rectangle. All right, so let's use a different color. Let's use orange. Right? So we're going to have midpoints. Let's do midpoints. And again, we're going to stick with this same example. We're going to use n equals 4, and we're estimating the integral of x squared from 1 to 5. Right, so again, visually speaking, I'm going to look at my parabola again. Where did my green go? My green disappeared on me. So I have my parabola, y equals x squared, and I'm going to exaggerate that shape. And then I want to go back to orange. Where's my orange? And then I want rectangles with the midpoints. So again, keep in mind, I'm going to go from 1 to 2, because that was my delta x, to 3 to 4 to 5. So in this first interval, I'm going to use the midpoint to come up and create the height of that rectangle. Then I'm going to use the midpoint between 2 and 3 to come up and create the height of that rectangle. I'm going to use the midpoint here to come up and create the height of that rectangle. Come on, draw a solid line for me. There we go. And then I'm going to use the midpoint here, 4.5, to come up and create the height of that rectangle. Right? So you can see the midpoints are going to be a little bit more accurate, because let's look at the second rectangle. I have a little bit of overhang right here. I have a little bit of underhang there. So I got a little bit of overestimate, a little bit of underestimate, and they should roughly cancel each other out. Not going to exactly cancel each other out, but they should roughly cancel each other out. So symbolically speaking, right, we have this integral is approximated by, and again, I'm going to factor my delta x out. So we're going to have f at 1.5, right? So my first midpoint was 1.5 that goes up to the function value. And then I'm going to have f at 2.5. I'm at a digital paper here. F at 3.5, and then f at 4.5. So there's the height of every rectangle at the midpoints for each subdivision. So again, from 1 to 2, midpoint is 1.5. I come up, find the function value at that point, so on and so forth. So our delta x was 1 for this particular example. And then our function is, y equals x squared. So I'm going to plug each of those into my equation, and I'm going to find y equals x squared for each of those x values. So I'm going to pause the video for a second, and I'm going to find that value. I'll be right back. All right, so I get 41 for that value. Right? So there's my calculator giving me that value. Let me go ahead and write that down here. So let me bring the calculator back up, and if we look at the calculator here, right, so on the top line, here's the value we just got, 41, and then the next line was us using the left endpoint that we did first. There was 30, and then the right endpoint was 54. So we can see, 41 is in the middle of those. Pretty much, right? Not exactly, but it's in the middle. So we can see, again, visually, right, that when we use the midpoints, we get a little bit of extra, a little bit of under, and they should roughly cancel each other out. So here's a good estimate to my integral. Right? Now again, what we could do is we could evaluate that integral. That's something that we could do pretty easily. I'm not going to take the time to do that. But what I am going to do is bring up a simulator, and we're going to look at this together. Right? So let me bring up my web browser. So in this simulator, right, this is the website. Let me see if I can bring this down. This is the website, geogebra.org/m/v75byej6. If you just did a Google search for probably like Simpsons Rule, applet, you should find that. Or you could just Google search GeoGebra approximating integrals. You should be able to find it that way as well. Now, so what I'm going to do here is I'm going to type in my equation, f of x equals x raised to the power of 2, and I'm going to hit enter. And there's my graph of f of x equals x squared. And then I wanted n equals 4. So I'm going to bump up to n equals 4. Now, the visualization that it's drawing for me is the right endpoint. I could do the Trapezoid Rule. I could do Simpsons Rule. And we'll come back to those and talk about those in a minute. If I go to position of 0.5, that's the midpoint. You can see that. Let me go ahead and draw the midpoints. Right? And then if I do the right endpoint, that's all the way to the right. Ooh, you know what? I just noticed a mistake here. So I want my left endpoint to be 1, and I want my right endpoint to be 5. So let me zoom out. I'm just using the scroll button on my mouse. Okay? So from 1 to 5, we're looking at the integral from 1 to 5. So we can see the exact value down here is 41.3333, right? So 41 and a third. And we can see that our midpoint, where was our midpoint? Our midpoint was the 41 that we got. And so down here, if I check this box, come on, if I check this box, I might have to go full screen. If I check that box at the bottom, it's going to show errors or not show errors. And I don't know why it's not participating, right? Probably on your computer, you can check or uncheck this box, and it says show error. So we can see for the midpoint, here's my error, 1/3, 0.333. Pretty easy to calculate. Here's my estimation of 41. Here's my exact value. I subtract those two, and that gives me my error. Now, if we look at errors, notice the error for the midpoint is 0.3333. The error for the left endpoint is 11.3. That's a lot of error. And again, it's an underestimate. as we see visually. And then if I do the right endpoint, that error is like 12.6666, right? So this is 12 and 2/3. This is 11 and 1/3. And then my midpoint is just 1/3. So we have much smaller error with the midpoint. So the midpoint is much more accurate. Now again, we have just spent about 20 minutes reviewing the concept from Calc 1. We're going to use rectangles to approximate the integral. Now again, obviously, I'm integrating y equals x squared. I would never want to do techniques of approximating to evaluate this integral. I would just take the antiderivative, 1/3 x cubed, and plug in upper limit minus lower limit. So the problems that we're going to look at in a couple minutes are going to be integrals where we can't evaluate them. Now, before we get to that, let's take a look at the last two techniques, which would really be the new technique. So we'd look at the Trapezoidal Rule or Simpsons Rule. All right, now I hate when my videos get really long, so we're a little over 20 minutes, and I don't want to derive the formula for you. We definitely could do that, right? I know how to derive the formula. I don't want to take the time to do that just for the sake of this video getting too long. So I'm pulling up Stewart's calculus book, right? This is James Stewart's calculus book. And he, in his section, he talks about the midpoint rule. And then the next thing he presents is the trapezoidal rule. And I just want to point out to you visually, right? Here's what a trapezoid is. So instead of a rectangle, we're building a trapezoid. So we still have the same delta x that we calculated in those first three examples. I would have a delta x, and I want equal delta x's. Instead of the left endpoint coming out and creating the rectangle, or the right endpoint coming out creating the rectangle, or the midpoint, we're going to do a trapezoid. So geometrically speaking, right, what's the height of this trapezoid? That's kind of what we'll think of, right? So the area of a trapezoid is we're going to take this side plus this side and divide by 2. So we're going to take this height, and we're going to average them. And then we multiply by the delta x. So when we come up here to Stewart's derivation, he says we're really going to average the left endpoint and the right endpoint. That's what he's showing me symbolically here. So for the first trapezoid, let's come back down to his picture. Here's the left endpoint. He denotes it as x sub 0. Some books call this a, right? A to b. But he denotes it x sub 0. Here's x sub 1. And the reason he uses x sub 0 is he says, this is the left endpoint. I haven't used my delta x yet. So when I add 1 delta x, I get to x sub 1. And then I'm going to add another delta x. So I've added 2 delta x's to get here. I've added 3 delta x's to get here. So if I take x naught and I add 2 delta x's, I'm here, so on and so forth. Right? So that's his symbolism. This is pretty standard for any calculus textbook. So for the first first trapezoid, the left side is f at x naught. The right side is f at x1. And we can see here's the area of the first trapezoid. And remember, we're doing 1/2 of that. We're averaging these two values. So in the line above, that's what he's showing you. I'm going to take the left endpoint, I'm going to take the right endpoint, and I'm going to average that. So for the first rectangle, that's what that looks like. For the second rectangle, I'm going to find the height at x1, the height at x2, and I'm going to average those. So here's f at x1 plus f at x2, so on and so forth. All right, so I'm going to have n rectangles that I'm going to utilize. So if you look at the last rectangle goes from here to here. So I'm using this last value. So with the trapezoidal rule, this is interesting, right? I'm going to use the first value, and I'm going to use this one, and this one, and this one, and I'm going to use the last value for this last trapezoid. So if I do the algebra of simplifying this, check out what happens. I only have f at x naught one time. But then I have f at x1 from the first trapezoid, f at x1 from the second trapezoid. So I have 2 of those that we would simplify algebraically. And then I would have f at x2 here, and the next one would have f at x2, and I would have 2 of those. And so on and so forth. So every y value has 2 until I get to the very last y value. So kind of the pattern that we have here is we have the first y value, then we have double every other y value, and then we have only 1 of the last y value. So the first y value is 1, second y value is 1 of them, and I have double all the others. So here's the trapezoidal rule formula, if you will. We're going to calculate our delta x. just the same way we always did, b minus a over n. And then this would be the formula, quote-unquote formula, we would use to evaluate the integral. So what I want to do then is let's come back and let's look at that last example that we had. Right? So we're going to look at the parabola. Right? I'm going to come back to my parabola here. Where's my parabola? It's not popping up. There we go. All right, so here's my parabola. Right? So when I'm looking at this parabola, I'm going to, in essence, use all of these endpoints. I'm going to use f at 1, f at 2, f at 3, f at 4, and f at 5. That was what the trapezoidal rule told me to do. So let me come down here, and I'm going to zoom out a little bit. I'm going to zoom out because I'm going to look at that same picture that we have there. Right? So let's do the trapezoidal rule. Right? Let's pick, what color do we want to use this time? Let's use purple. All right, let's use purple. All right, so I'm going to do the trapezoidal rule. So using the trapezoidal rule, right, here's what we're going to do. Right, we're going to say that the integral of x squared dx from 1 to 5, and again, we're using n equals 4 subdivisions. So my delta x, just like we did earlier, is going to be 1. So when we come back up to this graph, that was our delta x. We started at 1 because that's where our integral starts at 1, and then we add delta x, add delta x, add delta x, so on and so forth. So we're still drawing the same subdivisions that we did earlier. Now here's what the trapezoidal rule says. It says I'm going to take the delta x over 2. Sorry about that. Delta x over 2. And then I'm going to take f at 1. And I'm going to have double the next function value. So this y value, f at 2, I'm going to double that. And then I'm going to have double f at 3. I'm running out of digital paper. I'm going to have double f at 4. And then I'm going to have only a single f at 5. So this is what the trapezoidal rule says to me in that formula. It says I'm going to use this first endpoint, only one of those. And I'm going to have 2 of the y values at 2. 2 of the y values at 3, 2 of the y values at 4, and then a single of the last y value. Now, in the terms of the parabola, right, we know our delta x was 1. And then we're going to plug in each of those values. So we have the 1 squared, right? So our function is x squared. I'm going to have 2 times 2 squared plus 2 times my 3 squared plus 2 times 4 squared plus 2 times 5 squared. Oh, I'm sorry. There's a righto. Get it? Get it? A typo, but I wrote it, right? So there's a righto. So I have one of those. Right? So then I would need to take out my calculator and let's find that value. Or you know what, actually, instead of taking the time to plug that in the calculator, let me bring that website back up. And if we look at the trapezoidal sum, it gives us 42 as the estimate. So let me turn that graph off. Let me graph the trapezoid. And it's kind of hard to tell that it's graphing a trapezoid. Let me zoom in. Right? We can see here's a trapezoid. So it took the y value at the left endpoint, took the y value at the right endpoint, and it's plotting that trapezoid. Right? So if I zoom in, I can see each of those trapezoids. Right? And here's the estimation. So for this particular graph, y equals x squared, here's the estimation. And we can see the error that we obtained from that. So if I were to plug into the calculator, I'm going to get 42 as my estimation for the trapezoidal rule. All right, now let's do the other method of approximation. So the other method is called Simpsons Rule. All right, and again, for the sake of time, we're going to make this a little easy on ourselves, and we're going to come back to Stewart's textbook, and we're going to look at his example. So the Simpsons Rule, here's what the Simpsons Rule is really doing. So instead of fitting, let's say, a quadrilateral, or instead of fitting a four-sided figure like a rectangle or a trapezoid, we're going to fit a parabola to our curve. So you can see visually in Stewart's textbook, he starts with, the beginning value of my interval. He adds a delta x and he adds another delta x. So we got two delta x's. And if I plot those 3 points, that creates a parabola. So you can kind of see in blue, here's the parabola between those 3 points. And then we grab the next group of 3. So we start where we ended. We grab the next group of 3. So here's that y value, here's this y value, here's that y value, and we fit a parabola. So the concept here is that because the function is curvy, if you will, then the parabola is curvy, and it's a better fit. That's the concept here. Now, if we were to go through the algebra, this would actually take a little bit longer. Here's the parabola that we're using, right? Here's the parabola we're using to estimate that function. And if we were to go through all the algebra of finding those values, right? Here's where we end up. So here's Simpsons Rule. Simpsons Rule basically is kind of like the Trapezoid Rule, right? Remember what the Trapezoidal Rule was? It had delta x over 2. Simpsons Rule has delta x over 3, and it's because we have, the 3 values that we're using for our parabola. So that's where the delta x over 3 comes from. Now the midpoint rule, the Trapezoid Rule had 1, and then 2, 2, 2, 2, 2 is the coefficients, and then 1 of the last one. So again, if we were to take the probably 20 minutes it would take us to go through this derivation here, right, we would see where those coefficients come from. Right? And it comes from the parabola, is where that comes from. Right? So we're going to end up getting 4, 2, 4, 2, 4, 2, so on and so forth. Now, this is true for Simpsons Rule. The condition here is that n has to be even. The only way we're going to have enough data points to create groups of parabolas is that n has to be an even value. So in our example, we chose n equals 4, which is an even number. If the problem you're working on says you want to use n equals 7 subdivisions, that's an odd number, can't use Simpsons Rule. Have to have an even value of n to use Simpsons Rule. So let's come back to the example that we looked at, and let's use Simpsons Rule to evaluate that integral. So I'm going to pause real quick because I want to redraw the graph. I don't want you to have to watch that for me. I'll be right back. All right, so if I'm using Simpsons Rule, right, I'm going to integrate x squared. I'm going to approximate x squared using the formula that we showed in the textbook. So here's all of the subdivision values with a delta x of 1, just like we've been drawing in all the other problems. So it says I'm going to take delta x over 3, right, that's my formula, and then I'm going to take f at 1, and then the pattern is I'm going to do 4 times the next y value plus 2 times the next y value. I'm running out of room. Plus 4 times the next y value, and then plus just the last value. Okay, so here's the first y value, f at 1. I only have one of those. And then 4 times f at 2, 2 times f at 3, 4 times f at 4, and then just the single last value. So again, I'm going to pull up that formula in the Stewart textbook. And so here's our delta x over 3. We have 1 of the first values, 4 of the next, 2 of the next, 4 of the next. And we just repeat that pattern until we get to the last value where we only use 1 of them. So there's us plugging into that formula there. Now again, remember, for this particular example, right, my delta x was 1. So I have 1/3. And then technically I'm going to have, the function value at 1, 4 times the function value at 2, 2 times the function value at 3, 4 times the function value at 4, and then just the last function value. So again, I'm not going to plug all of that into my calculator. I'm going to bring up that applet that we were looking at. And if I look at Simpsons Rule, I see that I get 41 1/3. And I get 41.33333 as that decimal value. So let's say this is 41 1/3 if we were to add all of that together. And that's Simpsons Rule. So what's new in this type of conversation is Trapezoidal Rule and Simpsons Rule. Now, again, usually in the homework, you'll kind of revisit Calc 1, where you look at left endpoint, right endpoint, and midpoint. Now, if we come back to that applet real quick, remember that the value of the exact integral was 41.33333. Notice that Simpson's rule is exactly that. Notice my error is 0. I just want to mention to you that's not always the case. This beautiful parabola of y equals x squared, it works out that way. But in general, the Simpsons rule is usually the most accurate. And again, it's because visually we're fitting a parabola. Let me come back here. Right? We're fitting a curvy parabola to a curvy function. So theoretically, that should be more accurate. And we're going to see that that's the case. Simpson's rule is going to always be more accurate. All right, so I want to look at an application for you here as just kind of finish off this video. And remember, the beauty of mathematics is in its application. So we're going to look at a word problem. Now, I pulled this right out of Stewart's textbook. This in my textbook, it is section 7.7, where he introduces approximations to integrals. And this is problem number 30 in my textbook, right? So this is for Stewart's textbook 7.7 number 30. Right, now I'm gonna vary this problem a little bit, because in the problem all he says is use Simpson's rule, but I want to practice using trapezoidal and Simpsons. Right? Now if we look at the verbiage of this problem, it says the widths in meters of a kidney-shaped swimming pool were measured at 2-meter intervals, as indicated in the figure. Use Simpson's rule to estimate the area of the pool. So let's do both. Let's do Simpson's rule first, and then we'll come back and use the trapezoidal rule. Now here's the way I like to attack this problem. I am going to assume the first measurement here is a distance of 0. Okay? So I'm going to assume that this is a height of 0. This here is a height of 6.2. This here is a height of 7.2. This here is a height of 6.8, so on and so forth. And then this last value is a height of 0 as well. That's how I like to interpret this problem. Right? So I like to say the left endpoint is 0. So if we kind of think of an x-axis down here, this is the first value, second value, third, fourth, fifth, sixth, seventh, and eighth, and ninth, let's say, right? So he told us that these were measured at 2-meter intervals. So the distance between these were 2 meters. The distance between these were 2 meters. The distance between these were 2 meters, so on and so forth. Right? So in this case, my delta x is 2. Right? Here's my delta x of 2. This is a delta x of 2. This is a delta x of 2. Ditto, ditto, ditto. Right? Now, if I'm going to do Simpson's rule, remember one thing we said was Simpson's rule had to give us n equals an even number. So if we look at this, right, how many quote unquote rectangles do we have? 1, 2, 3, 4, 5, 6, 7, 8. So I technically have like 8 rectangles, if you will. I have n equals 8. That's what we have. Now, we don't really need to know that for this problem, but just to point that out to you, Simpson's rule needs n equals 8. So let's go ahead and do Simpson's rule. Right? Simpson's rule says I'm going to take the delta x over 3 as my Simpson's rule, right? And I'm going to take the first function value plus 4 times the next function value plus 2 times the next function value plus 4 times the next function value plus dot dot dot, and then the last function value, right? That was the formula that we had in the textbook. So my delta x in this case we said was 2. So we're going to have 2 over 3. And the way that I set this up, right, my first function value is a height of 0. And then I'm going to have 4 times my next function value, which was 6.2. And then I'm going to have 2 times my next function value, which was 7.2. And then 4 times my next function value, which was 6.8. And then I'm going to have, let me come down here, 2 times my next function value of 5.6, and then plus 4 times my next function value of 5, and then 2 times my next function value of 4.8, and then 4 times my next function value of 4.8 again, and then plus the last function value of 0. So there would be Simpsons Rule, setting up into Simpsons Rule formula that would estimate the surface area of that pool. Right? Now, remember, let me back up for a second because I didn't mention this, right? We're finding the surface area. If I scroll back up for a second, we're finding the surface area of this pool, right? We're finding use intervals to estimate the area of the pool. So remember, area is the integral of a function dx from a to b, right? That's our area in that case. So we're integrating this integral. We're evaluating this integral. We're approximating this integral. So to approximate this integral, we're using Simpsons Rule to make that approximation. I should have started there, right? We're estimating area. Area is an integral, and there's our Simpsons Rule. Now, if we look at Trapezoidal Rule, remember, Trapezoidal Rule is basically the delta x over 2, and then we're going to have f at the first value, and then we're going to have 2 of all the others. And then we're going to have just 1 of the last. So I'm going to basically repeat what we just wrote. Our delta x was 2, and then we're going to write down all these same values. But the only difference is we're going to have a coefficient of 2 on each of them. So I'm going to have 2 times the first, and then 2 times the next one, the 7.2, and then 2 times the 6.8, and then 2 times the 5.6. 2 times 5 was the next one, 2 times 4.8, 2 times 4.8, and then the last value. So if I were to plug those into the calculator, I would get the estimates. So I just won't take the time to do that in the video here. But if I were to take what do we have here? This top one was Simpsons Rule, and this bottom one was Trapezoidal Rule. So if I crunch those numerical values, I get the estimates to the surface area of that pool, right? So we're estimating an integral that finds the area, right? So estimating the surface area, we're evaluating this integral. And again, we don't have an equation for the f of x. We don't know what that equation is, but we have the function values for that equation. So, here's the height at this endpoint. Here's the height at this endpoint. So this is actually where the approximation techniques that we're talking about, this is where they will be most useful, is when we don't have the function. So usually what you'll see in the homework, in the word problems, you're not going to have an equation. You're going to have numerical data. So if I just pull up Stewart's book real quick, you can see that swimming pool problem. Here's the next one where they just give me numerical data. They don't give me the function, it's just the numerical data. They don't give me the function, it's just the numerical data. So the really interesting problems are going to be when I don't actually have the function and I'm using numerical data to estimate that integral. All right, so this video has already gotten way too long. Let me go ahead and stop here, and I will see you in the next video.